So I wanted to start with working through an example on generating a true time series data, right? Because when we're talking about this work, you have your source concentration, and then you have your receptor concentration. Source is usually unknown. That's what we're trying to predict, or it's some esoteric set of land and an average concentration in that. The receptor concentration is what's in that well. And then there's the true receptor. And so in that case, that's with no noise. It's exactly what's in theory happening. And then we have noisy realizations. So generating these data, you can do it in a lot of different ways. You can read in data. If you have, say, a modeling simulation or something like that, you can generate data, but no matter what, you need to interpolate the data to whatever frequency you're looking for. So in this case, here we're generating, I set up some weekly data or a couple of data points, then I linearly interpolate those onto weekly data. And then with pandas, it's pretty easy to go ahead and resample to monthly data, for instance. You can also, these detection power calculators, they run on an X value of years since the mitigation started, rather than date times, because date times can get all sorts of messy. And so you will need to transition to that, years since. And the easiest way I find to do that is to go from the date time and subtract the minimum and turn it into, and then go for days and divide by 365. The other thing I want to highlight here is the SciPy interp1d method, which can be a very useful way to do this. If you move into that years since approach early, you can just resample using line space or a range, not be a range, to set, say, at year 1, 3, 5, etc., every 2 years, for instance. And then the interp1d just allows you to pass the data in. So that handles that interpolation and that changing your frequency. In terms of setting up these, in terms of doing that analysis from the source, from the receptor concentration and predicting what those source concentrations could be, that Whakauru example, it's pretty simple. There is a function here, which is true time source from binary exponential piston flow. In this, you set your parameters, your H parameters. So it can be just, if you wish to just use an exponential piston flow instead of a binary, you just set frac P1 equal to 1. And then set your initial concentration, your target concentration, the previous slope that you want to match, and then some other limits. And you can generate these concentration time series just out of the gate. What this also allows is we can generate receptor concentrations over these time series from a complex source. And to do that, you need to use some of the groundwater age tools estimates here, predicting the future concentration and some other inputs. Once you read in the data and set up the parameters, pick the age inputs, and then we can generate the receptor by using our once and future concentration, that is what's happening at the source. And then you predict the receptor with just the predict future concentration and the age parameters. And then you can plot it up. And so if we take this age distribution and this source concentration, the resulting values are here. So that's all I really wanted to say about generating these true time series data. Does anyone have questions on that? Anything that needs clarification here? Patrick, feel free to jump in if you think I skipped something or went over something too quickly.
It was pretty straightforward at this point.
Yep, this one's pretty straightforward, and generally speaking, all of these worked examples are available. The code runs, so you can just go copy and paste and then edit as you need to be able to dig into.